Continuing our discussion about chemical equations, we want to talk about the idea of balancing equations. So when we have a chemical equation, we're really describing a process that involves molecules, involves compounds, involves atoms rearranging their chemical bonds. So when we write those molecular formulas, we really are describing molecules that are changing in a process. And so here is our description of the reaction that we've talked about. The C3H8 plus O2 becomes CO2 and H2O, right? Propane and oxygen becomes carbon dioxide and water. And these are the actual molecules that we're talking about. And so if we look kind of at the atoms that are involved, we can see, for example, so the black circles are carbon. So I have, say, I start with 1, 2, 3 in my C3H8. But then if I look on the product side, I only see one carbon atom. Okay, same thing with oxygen, just I have 1, 2 on the reactant, but now my product is 1, 2, 3. Hydrogen is my white atom. I end with 2, but I start with 1, 2, 3, 4, 5, 6, 7, 8. That is a big time change. And a large representation of what's going on, or a big time discrepancy of what's going on. We shouldn't be creating atoms. So as we said, the whole point of chemical reactions was rearranging chemical bonds, not creating or destroying atoms. What we have right here, how this equation is represented, violates what's called the law of conservation of mass. Atoms are just being destroyed or created. In the case of oxygen, we just end up with an extra oxygen atom, which shouldn't be happening. How we say this kind of in a lower level terms is that this equation is unbalanced. So this equation is unbalanced because you don't have a balance between the types of each atom. So the law of conservation of mass says that in a chemical reaction, matter cannot be created or destroyed. Right? And this was the problem of that unbalanced equation, that we were creating atoms or destroying them. So for a kind of life-size example, if we look at, say, 5 kilograms of wood, we have some wood and we burn it, right? We have a campfire and we would get some ash. But you'll note that we started with 5 kilograms and we ended up with 4 kilograms. That is not possible. You can't, that would imply that if we burned wood and we only got ash out of it, that would imply that we lost a whole kilogram of matter. And that doesn't happen in a chemical reaction. You don't just destroy matter. So where to go? Into the smoke, right? That smoke carries away mass. When you burn a fire, you lose mass in that smoke, which is good. We now have 5, but now that turned into 2 plus 4 is 6. So that's still a problem because now we've made more at the end, more mass. So where'd that come from? And that means it has to come from the air. A kilogram of oxygen from the air combines with the 5 kilograms of wood. We can see we have 1 plus 5, that's 6. And then we get 2 plus 4, that's 6 as well. So we started with 6 kilograms, we end with 6 kilograms. That's what the law of conservation of mass says. Whatever mass you start with has to be the mass that you end with. All of that comes together to produce all of that, all of the product, right? All the oxygen in the air, the wood, all combines to make all of the mass in the product. It's not saying, and you can certainly change what it looks like. That's the whole point of chemical reactions. You started with wood and gas, and you make smoke and ash. And so those are two, they look different, very different. Chemical reactions can change the chemical bonds. You can't make matter. So if we take a look back at the chemical equation we've used through all of this, we can see that there is this unbalanced or uneven number of atoms between the reactant side and the product side. I start with 3 carbon atoms in the reactants, and I get 1 carbon atom in the product. That is not possible in a chemical reaction. You can't just destroy 2 carbon atoms. They have to go somewhere. So we need to balance this, and the way that we go about balancing is by adding coefficients in front of molecules. What we don't do is change molecular formulas. You can't just say put a 3 right here and call it a day. You can't just say that there are 3 carbon atoms because that compound is carbon dioxide. There's only 1 carbon atom in a molecule. You can't just change the formula to make it 3 or 4 or whatever you want. So we can't do that. We need to put a number out front as a coefficient. What we're really representing by adding these coefficients is the number of molecules present. So you can see that the 3 goes out front. That's what I mean by coefficient. So just like in an algebra expression, if you have a number in front of a variable, say 3x, that means you have x plus x plus x. So here I have 3 CO2. That means I have CO2 plus CO2 plus CO2. We just condense it. Instead of writing all of them out, we just condense it by using a 3 out front. So now, when we go to count the total number of molecules, or total number of atoms for each type, I can see that on my reactant side, as we knew, we had one carbon atom, or one propane molecule. So there was a 1 coefficient out front. So just like with formulas, no number implies there's a 1, and each molecule has 3 atoms in it. You'll note that's from the molecular formula. We talked about that previously, talking about counting units and naming and all this stuff. So we have 1 molecule, each with 3 carbon atoms, and so there are 3 carbon atoms on the reactant side. Now on the product side, for CO2, because each molecule only has 1, what functionally happens is you make more than 1 molecule. You make 3 molecules that each still has the 1 carbon atom. But that gives you a total of 3 carbon atoms. Again, the chemical reaction doesn't change the number of carbon atoms, it just changes their chemical bonds. Instead of being linked together in this big molecule with hydrogen atoms, they're now broken apart into smaller molecules where each of the single carbon atoms is bonded to other oxygen atoms. We've changed the local bonding around the carbon. We haven't changed the number of carbon atoms. You cannot do that. So, by putting that coefficient in front of the carbon, you would have balanced the carbon. That needs to be done for every single element type in your reaction. So we dealt with carbon, you would need to do hydrogen and oxygen as well. And when we're going through the process of balancing, there's going to be more than one way to balance a given chemical equation. There is only one correct balanced equation, but there's going to be more than one way to get there. So what I'm going to talk about is an overall kind of approach that works for most equations, most chemical reactions, and kind of helps us just as a way to kind of get started and a way to work through it. Generally, you'll kind of develop some intuition the more you do this as to what a balanced equation does and doesn't look like. But for now, we want to use an approach where we work one atom type at a time. That is always going to be the best idea. So if we look at our sample equation, we have C, H, and O as our atom types. We want to go one at a time. And there is a better order that we approach those. First thing we want to do is we want to start with an atom that appears once as a reactant and once as a product. So what I mean by that is if, for example, we already did the C, we can see that on the reactant side of the equation, C only shows up in one substance. The other reactant substance doesn't contain any C atoms. Then on the product side, same thing. Only carbon dioxide contains carbon. There's none in the water. So that's an example that we would want to start with carbon. An example of what we would not want to start with would be oxygen. So oxygen is only in one molecule on the reactant side. But if we look now over on the product side, I can see I have oxygen and CO2, and I have oxygen and water. That means oxygen is going to be a difficult atom type to start with. We'll see where it comes up, but if you just think in that carbon example, or what we already talked about, you put a coefficient in front of something. If you needed to put a coefficient, you wouldn't know where to put it. You have more choices, so that's harder to deal with. The final thing we want to, so in this case, we would say oxygen's a bad place to start because it'd be hard to deal with. The next thing we want to look at is balancing elemental things last. And so when we're talking about elements, what that would mean is some sort of atom type that shows up in its elemental form. And in this case, it would be oxygen. So oxygen shows up in its elemental form in this reaction, right? That's not a compound. That is just oxygen atoms. That's going to be the best place to end. We always want to save elemental forms for last. So start with either carbon or hydrogen. Don't do oxygen. Oxygen needs to be last. So I want to actually balance it. So carbon and hydrogen, we could start with either of those, save oxygen for the end. I'm going to go ahead and do carbon first. We've already talked about it. When we start, what we can do is we can look at the fact of the number of each type of atom on each side of the equation. Carbon, we already saw on the reactant side, 1 molecule with 3 carbon atoms each. Product side, 1 molecule with 1 carbon atom each. That is not balanced. We need to put a coefficient. The coefficient, what we can basically ask ourselves is this is 3 and this is 1. You know, basically 3 divided by 1 equals 3. And so that means the smaller value, so there's only 1 over here, that compound, because it's the smaller total amount of carbons, needs a 3 out front. So 3 molecules times the 1 carbon atom. Now we would match up. We have 3 and 3. Carbon is now balanced. We can move on to our next type. We'll do hydrogen. So if we write out our equation, we want to find our hydrogen atoms. We can see that I have, the propane is still 1 molecule, but it now has 8 hydrogen atoms. So we have 8 hydrogen atoms total over here. Hydrogen only shows up in water. 1 molecule times 2 gives me 2. So I can see that I have more hydrogens on the reactant side than on the product side. I need to account for that. So I need to have more water molecules. I need to figure out how many. I divide the bigger number 8 by the smaller number 2, and I get 4. So I need 4 water molecules to get the total number of hydrogen atoms to be balanced. So now I can see that 1 times 8 is 8, and 4 times 2 is also 8. That's a hard number to write with a mouse. So I have 8 hydrogen atoms on both sides. That is now balanced. So carbon still balanced, hydrogen now balanced. Move on to our final atom type, oxygen. So we write out our formula, or the equation so far. We look for oxygen. And here's where we can start to see where oxygen was worth it to save till the end because of that product side, right? I got 3 molecules times 2 oxygen atoms, 4 molecules times the 1 oxygen atom. We can see that's pretty complicated in terms of all the places. There's just a lot of oxygen in the 2 different compounds. And when I'm looking at this product side, I need to add up both of those. I have oxygens in this carbon dioxide. I got oxygens in the water. Those are all oxygens. So I have a total of 10 oxygen atoms on the product side. If we had started with that, we would have not been able to guess that the coefficients you needed were 3 and 4. So definitely worth it to save oxygen for the end because it's complicated. We can see over here that this is a total of 2 on the reactant side. 2 is less than 10. So the reactant side with its 2 needs a coefficient. The particular coefficient is going to be 10 divided by 2, which is 5. So once we put the 5 in there, 5 times 2 gives me a total of 10 on the reactant side, just like I had on the product side. And so we work through our types of atoms one at a time. There's a better or worse order. If you had started with oxygen and kind of tried to piece through that, you could still have gotten to the right answer. It just would have been more difficult to get there. You would have had to redo work and recheck things like that. But you can still get there to the correct answer. There is just the one correct answer, but there's going to be more than one way to get there. So if we look at our overall balanced equation, we can see these coefficients, the implied 1, the 5, the 3, and the 4, imply the number of each type of molecule that is involved in the reaction. So 1 propane molecule reacts with 5 oxygen molecules to create 3 carbon dioxide molecules and 4 water molecules. So all of those are going to be created in this process, or used in this process and then created. And so one of the ways we can think about it is really, if you want to react one propane molecule, you need 5 oxygen atoms. You cannot do the reaction without those 5 oxygen atoms, because you need to basically deal, if you look at what the oxygen atoms are doing, the oxygen atoms take, you need 2 oxygen atoms for that 1 carbon, 2 oxygen for that 1 carbon, and 2 for that 1 carbon. You need 1 oxygen for those 2 hydrogens, 1 oxygen for those 2 hydrogens, that one, and that one, right? The oxygens go through and basically take up all these different atoms that you started with that need to be accounted for. So this is a lot like accounting. What all goes in has to come out. You got to balance that budget. You need to make sure that everything ends up where it's supposed to be. We can also always check a balanced equation to make sure that all the atom types match up. You have the work. We have the work that we did along the way. We went by carbon, oxygen, hydrogen. One of the things, as you work through, as you do more and more atom types, sometimes you can unbalance some ones you think you've already dealt with. And so that may be something you have to deal with or address. But you can always check at the end of the day, or after you're done, do I have the same number of each atom type on both sides of the reaction? When it comes to balancing, we want to have the same number of atom types on each side. That's the most, so a equation with the correct formulas, with the correct phases, and with the correct coefficients is the most correct representation. There are a couple other rules. These first ones we want to talk about make equations wrong. One thing we've mentioned before, but we'll say it again, you should not have any formula that shows up on both sides of the reaction. You cannot have zinc on both sides. 2 atoms of zinc becomes 1 atom of zinc is no good. It should just be 1 atom of zinc becomes 0 atoms of pure zinc, right? This top reaction is balanced, but you don't want to have zinc becoming zinc. That's not a change. That's not a chemical reaction. The real change is 1 atom of pure zinc, elemental zinc, becoming 1 atom in zinc sulfate, right? That is what we want to have as our description. The other thing we always want to be sure of, when you're writing chemical equations and balancing, the only numbers you put in are the coefficients. You can't distribute those. You can't put different numbers in different places. You can't put like a 4 inside right here. You have to keep the chemical formulas as is. You cannot change your chemical formulas in any way. There are also some conventions that are kind of surround chemical equations, things that aren't as hard and fast, but we do generally want to stick with. First thing is no fractional coefficients. Generally want to avoid these. When we're kind of conceptualizing chemical reactions, we're saying that whole molecules are reacting. You can't have half a molecule. So what you can do is, if you have a fractional coefficient, you just multiply by the denominator, and all of your numbers, multiply all of your coefficients. You'll see the 2 becomes 4, the 5/2 becomes 5, the 1 becomes 2, and the 3 becomes 6. So you're all still balanced because you multiplied all of your coefficients by the same number, but we do want to be sure that that is kind of, we're cleaning that up. See that fractional coefficients, you're not wrong. It just kind of looks not the best. And we'll see in other places, there are cases where they're used, but in general, we like to avoid fractional coefficients. Finally, we want to simplify ratios. You'll note in this reaction, we have 4H2 plus 2O2 becomes 4H2O. All of these coefficients are even, so they're all divisible by 2. So you can simplify it, get 2H2 plus O2 gives you 2H2O. Again, this top reaction, this isn't wrong. It's not wrong. It's still balanced. You have all the correct phases. It still all works. It's just kind of convention is to use simplified coefficients, where you've removed all of that from there. You can still use this in the right way. It's just kind of one of those things. Sapling might get mad at you if you don't have your coefficients simplified. All right, another video done. No questions for participation 611 in this video, but we're halfway through this set of videos. I'm sure there'll be more questions in the back half. See you there.